Here we go. Introduction to probability, okay? Taught this lesson yesterday. I like it because I teach this lesson before. I always kind of get the cobwebs dusted off my brain because it's been a whole semester since I've taught this. Excuse me. Statistics, introduction to probability. Well, let's just jump right in. So where are you going to see probability at? Well, obviously, one of the obvious things you're going to see it at, not for you, hopefully. Well, maybe one of us. One of us can go to the casino in here. I'm not going to throw anybody under the bus. Just saying. No, but the rest of you probably haven't been to a casino yet. Okay. But you know about casinos. We're not stupid. Okay. But that's where probabilities happen a lot. Okay. That's where you see it happen a lot. And that's where you hear about it. People talk about it. You might even think about the lottery or the Powerball. That's probabilities. Okay. But there's a lot of other places probabilities are running all the time. Matter of fact, I would say that statistics is based mainly on probability. Okay. Because I would say that whenever I take a sample, and as you will learn to take a sample later on, do I know everything about the population at that point? No, I just know about the sample. So I'm saying by this sample, there's a probability this sample matches what I'm seeing in the population. That's kind of how it works. Okay. Where else might you see it? Carnival. I love going to the carnival. I will never ride a ride because I don't trust it. Okay. I don't trust anything they can throw up that fast. Okay. Ran by people that smell like cabbage. Not happening. Okay. But there are probabilities. In fact, whenever we get to lesson 4.2 and 4.3, I've actually pulled some carnival questions. Okay. Actually in your book, but I actually go to the carnival because I'm that kind of a weirdo that I actually like to go and see. I will do like little experiments, write down things, do some little math things. You know, it's fun. It really is. Anybody else think, where else might you see some probabilities happening? These are kind of the obvious, but where else do you think? Have any idea? How about your phone? How would your phone have a probability with you?
Is that what you were saying, like the ads that, depending on what you've looked at, it develops ads?
Your phone, nothing knows more about you than, there's two things that know about you completely. God and your phone. Okay? Because your phone, you put everything in. Every text message, every secret desire, everything you search. Even when you think that you're searching quietly on incognito mode and you're thinking, surely nothing's going to happen now. Oh, yeah, because why would they that's just a word. Do you really know it's incognito mode? You ever thought about that? So it's sitting there running all these things on you all the time, and it's building up these thoughts and not thoughts, but it's a computer. It's building up all these things about you, and then it says, hey, I think he likes to wear pink leopard jumpsuits. Okay. And so it's going to send him a link saying, wouldn't you like to wear pink leopard jumpsuits? And he's going to just ignore it because he's like, I don't like pink leopard jumpsuits. And so the machine took a guess. It took a probability and said, oops, a lot of people in his demographic like pink leopard jumpsuits. He doesn't. By him not answering, he fed the beast. Okay. And so, but when it answers like, do you like what kind of shirt is that? Columbia or something like that? Yeah. Do you like these type of clothes? He's like, I do. Matter of fact, I was just talking about that with a friend. Oh my goodness, my phone is reading. No, it's not. It's running probabilities. Sometimes it gets it right. Sometimes it gets it wrong. The more it knows about you, the better it's going to get. Okay, so that's how those are, and there's a million other ways how it's running probability. That's just one of the simpler ways to explain it. Not getting a ticket, you can't, I don't want you to look at this and go, okay, so what's the probability of me getting a ticket today? Probably some of you, a lot. I've seen some of your driving in the parking lot. you have a very high probability of getting a ticket, okay? But what I'm talking about is your insurance. Did you know your insurance is based off probabilities? How? Younger? Driving history? How's that probability though?
They say like guys are more reckless, or more probable to be reckless drivers.
Did you hear that online? He said guys are more reckless and prone to be what more. Like more reckless and more just like crazy drivers, okay? Is that fair? Are all the guys, I see some girls, yes, it's very fair. It actually gets deeper than that. I have a friend who became an actuary, okay? An actuary, and it's something I actually wanted to do until I realized that I didn't want to put a price on death. Okay, because that's what an actuary does. They put a price on, not just that, but the one I was looking at, it was like really, hey, how much can we charge you per month? So if you die, we can pay your family and they'll shut up. And also we make money. So how much, does that need to be? And it's a whole bunch of probabilities. It's saying not just your age. Oh, no. Your insurance is based off the probability of where you live, the city, the probability of your age and people in the United States. And then they don't just go to the United States, they'll go to your city. And then they actually get so close, they'll go to your house and go, we're going to charge you more because he drives bad. That doesn't sound fair. But the probability of him hitting you, we got to think about that. So all these little probabilities are rolling in together. And then there's people out there that literally take all these probabilities, they run experiments and go, okay, for you, this is what your quote is. Because this is the probability that if you get in a wreck, we'll still make money. And then what happens when you get in a wreck? Your insurance is like, hey, no worries, we got you, right? But then what do they do next month if you ever been in a wreck? They up your pay. Because now, guess what? Now you're not a risk-free anymore. Now you get to be in a new type of probability that says, hey, now you're in this new one. Now you're somebody who's gotten into a wreck. Now instead of you being the neighbor who got in a wreck, you're the person they're basing this person's. So notice how that's weird. It's all probabilities. So they're everything. Probabilities are everywhere in your life. When I first learned about them, I was like kind of amazed. It's a deep, deep, deep rabbit hole. Believe it or not, if you're seeing this picture, and for any older person, me and her included, everybody in this picture except for this man right here, okay, is below 25. Welcome to the 80s. That's how people looked in the 80s, okay? When you see all these pictures of like, neon and stuff like that, nope. That's the 80s right there. That's how it really looked, okay? People looked like they were 95 and about ready to retire when they were graduating high school, okay? And they had gun racks and they smoked cigarettes in class. I'm just joking about that part, but still not about the gun racks. I actually have friends who would go hunting in the parking lot in my school. They would literally go outside, go hunt rabbits, and then go back to class. Okay, but this right here is a perfect example of probabilities. This is a movie. I'll show you the movie. It's got unfortunately, a actor who's gotten in trouble by a lot of stuff. But then I kind of thought about it. I was like, should I remove this slide? But I'm sitting there thinking, name an actor who hasn't done something weird and stupid in the last 3 days. So I was like, whatever, keep it. But this is the MIT blackjack team. I'm just saying MIT, you never thought of blackjack. But what it was, the professor, I will not be doing this, by the way. Okay, the statistics professor found some highly motivated students and realized that he could use a system created by another guy way prior to count cards in a casino. What it basically was, he would go to a casino because he realized that blackjack was the easiest game to beat in a casino. And he did what he called counting cards. You can go look that up on how to count cards, okay? It's not illegal at all. But the casino will kick you out, okay, if they find out you're doing it. Okay, because of these people right here, they started using facial recognition software in casinos and actually share it amongst all casinos in the world. But they became a team, okay? So one person would be the high roller, one person, they each had their basic parts, okay? I think before the casinos caught on, if I'm correct, I read the book, I think they made something like $45 million off the casinos. Okay, so the movie, if you ever want to see, it's called 21. It's highly dramatized, okay? If you actually read this real story about some of the real people who did it, it was actually kind of boring. They said, they go, man, we'd sit there for 9 hours, but they would play a part. Like, he's my nerdy guy, but guess what? Today, you gotta be the high roller. So they would go buy him like Armani suits, $30,000 watches, and he walked in there and they'd hire girls to walk with him. So it looked like he was this high roller. So what would happen? The casino's like, hey, come on. But he was a card counter the whole time, running math in his head. So it was actually kind of ironic. So pretty interesting movie, but it's one of those movies that it does highlight probabilities a lot and how they can be tweaked to your favor a little bit. I don't recommend it doing it. Casinos are very, shall we say, aggressive when they decide to remove you from a casino, when they find out because they'll consider it cheating. Really not. But still, they do consider it cheating. So, what does random mean? Y'all say it. You've all said it to somebody now, like, that's random. Remember that? Well, what does it mean? What is random? Give me a definition of random. Can't be wrong.
Odd, out of place.
Odd, out of place. Okay, I like that. What else? Give me another one. She broke the water. Somebody else give me one. What's that?
It's like when you said that a computer randomizes, it picks out numbers. There's no specific order or pattern to them. It's just picked out.
Okay, no specific order. Odd. No specific order. Anything else?
You can be randomly selected.
Randomly selected, like,
A bunch of people, you just randomly just pick.
there you go, there you go. Oh, let's think, I'm not gonna answer it. Let's think about it. I want you to think what random is. Now, there's mathematical definitions, there's, how I told you about how we do samples, random. What do we mean by probability? Random. It's something to think about, okay? Now, let's get into the nuts and bolts real fast. I want you to just keep thinking about that random. A lot of things you're gonna learn in this class, like even this right here, I'm not gonna answer it. I want you to think on, what does random really mean? Because I could argue with that one, something that's odd, is that random? But if enough things are odd, are they really random anymore? Or do they become normal? And is the computer really random, or is there some sort of algorithm that accidentally is not working right? Is a dice random? Is it? All the time? Why in statistics are you gonna read a lot in this class? A random fair die or fair coin? Why not just say coin? Kind of makes sense, doesn't it? Maybe something to ask about. Somebody's got to flip a coin. You should ask, is that a fair coin? What about weighted it on one side? Is it random anymore? Good question. Let's get into the nuts and bolts. Probability experiment. What is a probability experiment? Well, let's use coins still, okay? We know that a probability experiment, now hear me out, experiment, I'm gonna say that word very specifically, experiment, says this, or it's a trial, says it's the act of doing something, okay? It's an experiment. We all know what experiment means. So for us, the experiment is going to be flipping a coin. Sounds good, right? Outcome. What do you think an outcome is? We know what the experiment is right now, right? What's an outcome?
A result of the experiment.
A result, right? A result. So if I flip a coin, what's my possibilities?
Head and toes.
Heads or tails, right? I can't get like a 1. Can't flip a coin and get a 1. That's kind of a duh statement, but kind of makes sense. So you can say it's the result. Now, what's a sample space?
Possibilities that you have.
Possibilities. Think back, if you took intermediate algebra here, one of the first lessons I ever teach in intermediate algebra is sets. Okay, when you have a set of something, it's all the possible things, all the possible answers in that thing. Well, that thing is all the possible things that could happen, which I'll be honest, is usually the hardest part about statistics. It's finding out all the possibilities. Okay, that's the hard part. What you want to happen or what you need to see or whatever happens, that's usually the easy part. It's the outcomes. So sample space would be, for this one, would be what?
Heads or tails.
Yeah, heads or tails. Keep it simple. Heads or tails. That's my sample space. So it would be an H or a T. I get a heads or a tails. We do not count the probability that 1 in 1 billion chance that you flip a coin and it lands on its side. Okay, I've never seen that happen ever. You can Google it. It'll happen on YouTube, and I guarantee you it's fake. Okay, so event. Here's the event. I'm gonna show you how it's gonna be seen for you, but it's literally what you're wanting to see happen. So what is the probability of me getting a heads? Okay, or the probability of me getting a tails? Okay, we write it in this form. P, always probability, kind of an italic P. And we're just gonna put, I'm gonna put a heads. It'll be P of H, probability of getting a heads. You'll actually see some where they'll put P, parentheses, and they'll write a sentence in there. Probability of me walking to my car and getting hit by a blue Chevy. Okay. Is that 0%? No, could it happen? It could. The probability is just what? Extremely, extremely small. But if one of you drives a blue Chevy, you might be thinking, could make a bet on this. So there you go. Good so far. So we know the trial, we know the outcome, we know the sample space, we know the event. Well, that's all fine. Let's see an example here. So here I have the probability of an event. Obviously, I've got dice, all the possible ways, all the faces of a fair dice. Okay. Good. Sorry. So I have this probability of this event happening. We don't know what it is going to be yet, but we know that this part right here, that stands for the probability. This part stands for the event. And by event, it's what event do you want to see happen, or the event you're studying, or whatever. Okay. I'll say it interchangeably, and I've been trying to weed this out of my vocabulary, and statistics teachers are really bad about this, me included. Okay, I'll take those sins on myself. People will say favorable event. Well, I don't like that, because I would rather say the outcome of the event I want to see or that I'm measuring, because what if I'm doing the probability of me getting cancer? That's not really a favorable event. I don't want to get cancer, so let's not call it a favorable event, but maybe it's the event I'm studying. Now, does that mean I'm not going to say favorable event later? I probably will, but I don't want that to cloud or muddy the water whenever it starts saying, hey, studying this and this person getting sick, that's not very favorable. What do I need to look for? It's not just things we want to see. It may be things we don't want to see happen. Okay. So what's the probability? Notice I just put a number there. What is the probability of getting a 6? Now, as a hint or help or whatever you want, what I would do first, what are all the possible outcomes? I'm rolling a dice. And this does help, I promise you. If you tell yourself a story, 4-1 through 4-5 is all going to be about personal storytelling, not just reading the problem. If you put yourself into it, it'll make a lot more sense. This kind of math you're about to do is not intuitive, okay? It's not going to be something like in college algebra or intermediate where you went like, I was flying in a plane. How fast was I going? And if you got like 1,000,000 miles, you're like, I did some wrong math. That's not going to be the case here. Probabilities don't work that way because we don't intuitively think about them, okay? They're not something we live with thinking about on a daily basis. So put yourself into the story. First off, I'm rolling dice. How many dice rolls could I have? 6, there they are, right? I could roll a 1, a 2, a 3, whatever. So whenever I do these, I always go, okay, the probability of a 6 is equal to, well, something over 6. 6, okay, that's my outcomes. That's my outcome space. All my possible outcomes is gonna go on the bottom. All outcomes. How many ways is there to roll a 6?
One.
Exactly. So that's outcome. Looking for. Stayed away from saying favorite. Now, to save you some time, Hawks is gonna tell you this. Hey, put this either in simplified fraction form or, okay, put it into a decimal, okay? And when we put it into a decimal, I'm gonna tell you this shortly, it'll show you on the slides, but it'll actually say round to 4 decimal places when dealing with probabilities. It's a rule. So that means you're gonna need to look at the 5th number to round the 4th, okay? I tend to just always go decimal. Reason being, 1/6 looks pretty nice, doesn't it? They're not all gonna be 1/6. You're gonna get some pretty big numbers. Why spend the time trying to figure out how to reduce those fractions down and get a blue bar when you can just go ahead and do the division, give me the decimal, and be done with it? Okay, really honestly, your choice. I'm gonna take either question. I'm just trying to save you just a little bit of time, okay? This one right here, I'm gonna put on this side. If I did it as a decimal, it'd be 0.1667. Hawks will probably never ask you for percents unless they did an update and change questions or change formats of questions. Can anybody tell me how to change that to a percent? What's your mathematical way to change that to a percent?
It's about 100.
Times it by 100. Move the decimal 2 places to the right. If you need to change it to a percent, okay? To change it from a percent to a decimal, we divide by 1. Kind of remember that from that lesson where we did the percentiles? Okay. So yes, this right here would be a 16.67% chance. So so you're with friends, you're rolling dice. You bet your friend, hey, bet you $100, you don't roll a 6. Okay, or you're gonna roll a 6. Well, you just bet $100 on 16.67%. Okay, there you go. I'll show you later on in another chapter if that's actually a good bet. Well, what's the probability here of rolling the dice less than 10? First off, we could put in here probability of what? Less than 10. Well, what would be my bottom number still?
6.
Okay, what's my top number now?
6.
6. Because aren't all the numbers less than 10? Yeah, so what's my probability? 100%. Kind of makes sense, right? That underlies something. That would also be 1. Okay, 1 is the same as 100%. What if I change this around to what is the probability of rolling greater than 10?
0%.
What would I write that as a decimal though? How many outcomes do I have?
6.
What's the top number?
0.
0. And 0 divided by 6 is always.
0.
So good to hear that, instead of having to teach that to people. This is an underlying rule of statistics that probabilities, okay? Probabilities can be no less than 0. They start at 0. Okay, and they go to 100%. You cannot ever, I will laugh to myself if I ever hear anybody of you say this, because you've heard me say it now. You cannot have greater than 100% probability. Okay? You can't be like, I think there's a 200% chance this is gonna happen. That's stupid. Okay, it's only 100%. Now, you can have 110% profits. Okay, for you micro and macroeconomics people, but you can't have, what is the probability of this thing happening? It'll never be greater than 100%. Because 100% means something happened, right? So let's think of it this way. I flip a coin, what's the probability of me getting a head? I get the head. How does it become any more than 100% than that? Let's say I flip a coin that has two heads. And I flip a coin and I get a head. Isn't that kind of a duh statement? I'm gonna get a head. Is there any way from anything, can I get more than heads? Can I get a bigger head? That doesn't make any sense, does it? So no, it's 100%. It's either 0 or 100%. Now, I say that things are gonna get infinitely close to 0. Things are gonna get infinitely close to 100. But very rarely, except for right now in these very specific times, like this one, okay, will you see statistically when doing experiments 100%, 0%. Things will be like so close to 0, you might as well count it as 0, like 0.0000 some number. That might as well be 0% at that point. That can help you all understand that a little bit. Okay. There's your sample space. Notice I described it like a set. When we're looking at a probability of 6, there, 6 is the subset of that set. I'm showing you pictures because later on, I'm gonna start drawing some pictures and it's gonna help you a little bit, do some more understanding, especially in 4.2. Okay? Notice less than 10. What would be my, first off, same sample space, right? I'm still dealing with the 6 rolls. But then what? What would be my subset of that? Everything, right? So that gets into a rule about sets that I won't go into in this class. Let's run a probability. I want you to figure it out. Let's run a probability of tails. That means I'm going to flip the coin and get tails. And odd die. Give me the probability. Figure it out. I give you the sample space. I give you all the possible outcomes, don't I? Okay, so look at it carefully, and then I'll help you. Yeah, I'll literally give you about 30 seconds. I want you to kind of see if you can figure it out. My event is, what is the probability of me having a quarter in my hand? I flip it, and I get tails, and then I roll a dice, and there's odds. Okay? Good? You might be right, you might be wrong, I don't know. First off, you see where there's tails, you see odd numbers, right? Let's look at it this way. How many outcomes? Remember I said, how many outcomes do I have? Count them up. 12. 1, 2, 3, 4, 5, 6. How to? I don't want to, I want to be lazy. Yeah, I've got 12 here. But now you have to look at it this way. Right here is the only way I can get tails, right? But then I'm taking this universe of 12. Okay, so in my outcomes, I look at the whole universe. But then what I'm looking for, okay, I'm now narrowing my universe down. So my first narrow is to go, what's happening with my quarter? I'm only allowed what? The tails. Okay, so I've narrowed it into that. But now I've narrowed it in even more to what? Odds. So I can only have tails and odd numbers. So I come in here and go, how about here, here, and here? So 1, 2, 3. Which is equal to what? Which we know would be 25%. So that's saying, if you flipped a coin and got a tails and then rolled a dice and it was on, the probability of those two things happening, okay, 25%. That can help you see it? Okay. The outcome is usually the hardest part. Okay. Now, and as one of my statistics teacher told me, remember the bottom number, your denominator, that's your universe. Those are all the possible things that could happen. Everything. Your top number, your numerator, that's where your universe has been shrunk down. What things am I picking out from my universe that I want to see materialize? What events am I looking for at that point? Okay, and those go on top. Another way to look at this is like this. We're gonna use flipping a coin again. What's the probability of me getting heads or tails right now? 50% makes sense, right? But what if I said to you, hey, what's the probability of me flipping a coin and getting a heads and then flipping a coin and getting another heads? There you go. Because couldn't this happen? I flip a coin, right? I get either heads or tails, right? Either head or tails. That's the only possible thing. Well, if I get a head, I've got to flip again. Well, what's going to happen again? Heads or tails? What if I did it again? Notice it just kind of keeps, you see a pattern here? Look at this. How about 2 to the power of 1? 2 to the power of 2. 2 to the power of 3. What's my outcome space? Isn't this the outcome space right here? Okay, so let's think about it. Okay. If we were running an experiment, okay, and for this right here, okay, that's your number of outcomes. That's your trial number. Online, and some other people may explain differently. I like this way because it makes sense to me. Like, remember, number of outcomes. I can only have heads or tails. That's it. I can't flip a coin and get a 6. There's only heads or tails. So with my first trial, my outcome space is literally that. It's 2, because 2 to the power of 1 is 2. If I decide to flip the coin twice, I have now added on to that. So my second trial is going to be 2 to the power of 2, which would be 4. Notice I showed you that on the decision tree. I say this because I don't know, it might make its way onto a midterm. Just saying, hint. I might ask you, what's the probability of getting, say, all heads? Let's look. What is the probability of getting all heads? After, say, 3 trials. Well, isn't that my sample space? Because look at it, if you follow the tree, there's a head, right? There's a head. There's a head. So how many ways is there to get all heads? Yeah, how many things are in your sample space? 8, right? And there's only one way to get all heads. Now, to be honest, when and if I ask you this on a midterm, I'm not going to ask you, hey, what's the probability of you getting a tails and then a heads and then a tails? That's a little bit beyond, well, not really. There is a way to do it, okay? But we won't do that on this midterm. I try to keep the midterm very, very simple. Okay, it's actually pretty sweet in the midterm. Does that make sense to you? What I just did there? Not horrible, is it? Like I said, it's probably harder to figure out the outcome space than it is anything. Okay, but here's the thing. If we did the math to that very quickly, I should know this, bad math teacher, my bad. But 1 divided by 8 gives us 12.5. So I'll put this up here, 0.125. But couldn't I change that? Let's think about it this way. If you're pregnant, what could you have?
A boy or a girl?
There you go. That's good, right? A boy or a girl. Okay, so she has a boy or girl. We don't know which, but we know the odds. So all of a sudden she's going to have a second child. What's the probability of it being a boy or a girl? How much? It's still 50%, right? Because notice it didn't change the previous thing. You're still going to have a boy or a girl. So, okay, you go along a couple of years, you're like, okay, fine, one more. We're gonna have 3 children, bam. What's your chances of having a boy or a girl? Still 50%, right? But notice how I can change that. What are the odds of you having all boys after 3 turns? 1/8. So there's a 12.5% chance that you would have all boys. Or you could look up here and change the, like if the boys are the heads, the girls are the tails, what are the chances that you would have a boy, boy, girl? In that order. Boy, boy, girl. Or boy, girl, boy. You can look at percents. I have a pastor friend. He has 6 kids. Yeah, I think they're going for a 7th. More power to it. Okay? They're all boys though. So what do you think the odds of that are? I mean, I've told him, I go, man, if you have another boy, bro, you need to start playing the lottery or something, because really the odds of it, well, look at it. If you're gonna do 2 to the power of what, 7? Figure that out. I'm not gonna work it out right now. The odds of it are pretty small. Does it mean improbable? Does it mean it can't happen? No. It's like, is there a possibility it's not gonna happen because it's actually gonna be 0% because I don't go? But could it be possible that I walk over to the casino today, put $1 in a machine and win $30 million and retire? Could that happen? Is it gonna happen though? Probably not. Okay? But is it possible? Yeah. Look on the internet. Somebody right now just won a big lotto something, right? So there you go. That probability is out there. Okay, so that is how that works. Are we good so far? Oh, doing great on time today, so. 3 different types of probability. Subjective is the easiest one. I'm not even gonna give you an example. I'm just gonna tell you what it is. Anything that starts with I think or I believe. You all do it. What are your chances? Hey, bro, what do you think the chances are that she lets me take her to the dance? I think I got about a 60% chance. Is that probability based on any type of anything like scientific research, anything? No, you're just kind of going, I think. Like, now, let's be honest, like, let's say you've done 0 homework so far. You're like, what's the probability I pass this class? And you're kind of going off some experiment, but it's still kind of just a guess, right? You really don't know. Okay, so that's what subjective is. Okay, it's really a belief that's really backed up by, I'm going to say nothing, but I want to always realize that if you think about it, when you have a hypothesis, if you're a professor like me or like a scientist or somebody, it kind of starts with a subjective, like I think XYZ. But then what happens? Then the experimentation starts. You know, when it's just among friends, that's kind of crap subjectivity. But if it's happening in like a kind of like step-by-step process where you kind of see things happening in nature, like for example, Isaac Newton watching things fall. I think there's something called gravity, and I think I can put a math equation to that. What's the probability of that? You know, whatever. That's a hypothesis. He's thinking of something. That's subjective. But then it became what? Rigorous proof later on. Okay, that's kind of how things work. Experimental, though. That's the fun one. Let me give you a formula. Here it is. Experimental probability says this. If E is an event, then the probability of E, read the probability that E occurs, is given by P of E is equal to F over N, where F is the frequency of event E, and N, little n, is what? What is little n in this class always? Sample size. Well, why would I be doing sample size for a probability? Let me show you, okay? Let me show you this part right here. There's that rule I was telling you about, the probability, the rounding rule, okay? This is an experiment. We're gonna keep using the coin because it's easy. Easy math, right? We like easy math right now. I flip a coin. What is the probability of me getting ahead that you know of? 50%. Okay, but Let's say you didn't know that. So I flip a coin. I have flipped a coin how many times? So we're gonna say heads. Let's go the probability of getting a head. And this is gonna be trial number 1. I flip a coin, the probability of me getting a heads, I flip it, I catch it, I look at it, and it's a heads. Well, guess what? The probability of me getting heads at this point is 1/1, which is 100%. Right? Because think about it, N is the number of trials. 1, the frequency, is the event I'm looking for. Well, I'm looking for heads, right? I got it. So if you knew nothing about coins, you might say, sweet. That coin's pretty nice. Well, let's do another run. I do it again. We're at trial number 2. Probability of heads. You can't change your experiment. You got to keep going with the same direction with it. I do it, I flip, I get another heads. Nice. So now I'm sitting 2/2. Still 100%. Or remember how you'd be putting in Hawks 1, 1. I do it again. Let's do one more experiment. So now we're on our 3rd trial. Probability of head, and finally I got a tails. Well, now, how many times have I gotten a tails? I've only got a tails 1 time. So now though, I wasn't looking for tails, was I? How many times have I got a heads? Twice. But how many times have I ran my experiment? Notice, so now I'm sitting at 0.66 or 66%. Flip those by accident. Still, do you get what I'm saying? This is an experiment. Okay, and I get it, you're saying, but the coin said no, but the experiment is saying this. Okay. Good so far? Well, classical says this. Classical says this, you know the specific number. I'm going to demystify what this is saying. We know that a coin has how many possible outcomes? 2. We know that. 100%, we got it. So that's what that's saying. What's the actual number in the sample space in classical probability? Well, we know it's going to equal 2. Then what it says here, the number of outcomes in the event, well, we know you can only have one outcome. How many outcomes when you flip a coin?
Or 1.
1. When you flip, you can only have one outcome happen at a time. I can't have heads and tails at the same time. I can only have one. So classical probability says it's a 50-50 chance. Okay, 50%. Anytime, just as an FYI, anytime you hear any probability getting really close to 50%, you'll hear news anchors, people even like me. I've even said at home, talking to my wife about weather. She'll be like, hey, there's a 48% chance of snow today. That's a coin flip. Why would I call it a coin flip? Because it's about 50-50. Okay, so when you hear that term now you know what that means. It just means, oh, it's a coin flip. Who knows what's going to happen? You know? So we know this is equal to 0.5 or 50%. That's the classical. Now, to address something, not everything has classical. If I'm testing a brand new drug that I've created to help see if it's going to help, you know, that I can eat all the Twinkies I want and not get fatter, like first off, do that, dude, I'm going to be balling. Okay, I love Twinkies. Okay, as it shows, especially on that camera over there. What? ITV lets you know how fat you are. So been going to the gym more though, trust me. Anyways, there's no classical to compare that to. Does that kind of make sense? Whereas with dice, some things we can compare it to a classical probability. Dice, coins, some carnival games, blackjack, roulette. Some things have a classical. Okay. I know this because like casinos are big on classical probability. There's no game at a casino where I'm going to walk up to you and go, okay, guess my favorite color. And no, that's, how are you going to make money? How am I going to make money? That's subjective and I could change things. No, they want hard numbers. Okay. They can still kind of manipulate into their favor. Good so far? Okay. Let's run an experiment. Open my casino. Okay? It's a nice casino. We use really, really busy carpet, as you can see, because people throw up a lot. And so I don't want to change the carpet, so I'll just keep busy carpet. Okay? So you are sitting there like the creeper that you are and are watching somebody. So you've been sitting and watching this person play a certain slot machine for over an hour. Okay? They played 313 games and they've only won 28 times. And that was only during the first 20 minutes or so. So basically they've lost for how long? 40 minutes. Okay? Let's run an experiment. What is the experiment? What is the probability that you are now going to go sit down at that slot machine? I am not, just by the way, condoning gambling, because when this makes it online, I don't want deans and people and parents going, this statistics professor was telling people to go gamble. Actually, this should show you that I'm telling you not to go gamble. You're about to see shortly. What's my outcomes? What's my outcome space? But how many times did the thing happen? How many trials did we run?
313.
Yeah, 313. We ran 313 trials. Now this poor little old lady just spinning away her retirement. Okay, didn't know that you were running an experiment and she was part of an experiment, but you were counting every time with a little clicker going, all right, lady, click, click, click. Okay, but she won how many times? What was the outcomes you were looking for? 28, exactly. When you do the math to that, okay, you get 0.0895 or 8.95%. Maybe I should have wrote that in white. Now you can see it. Okay. So what is the probability now that you're going to sit down at this slot machine after she leaves, because you're watching the moment she leaves, you're jumping right in. Okay. What is the probability that you're going to sit down and start winning? 8.95%. Does that sound about right? That's your experiment. That's your experiment. That's what your experiment tells you. I have about an 8% chance of winning, which, knowing what you know about casinos, you're sitting there thinking, that's some pretty good odds. You know? Let's look at the classical. Classical says this. Now, I want to be transparent with you. First off, every single slot machine at a casino is different. They have different odds. Okay. Every state has different rules. And it depends on what you decide on winning. So let's go ahead, as anything should happen. Let's decide what we consider a win. Okay. So we'll do it both ways, just so I can show you. We're going to consider the first way as a win. And what the casino considers a win is this. No matter how much money you put in. So if you got $100, you walk up to a quarter machine and you put $100 in that thing and you hit play, whatever it is, and it pops out a quarter. You just won. It counts that as a win. Good job. Okay. The odds of you winning any slot machine as set by most states is, are you ready for this number? A win, how we just classified it. That means you just won a quarter or a penny, whatever machine you're playing. 1 out of 5,000. Okay, that means you actually have, let's put this in percent, a 0.02% chance of winning. Let's look at a jackpot though, because that's really what people play, right? Are you going to win quarters? No, you want to win the big money. Okay. On the lowest level machine they have, I'm not going to tell you which one. Okay. It's 1 out of 34 million of the lifetime of the machine. So your chance of winning that is 0.0000029%. Sounds like a winning thing to me, don't you think? That's where I wanna go put my money. You know? It's kind of weird thinking of it that way, huh? Now, let me show you something. Here's a rule, and I'm about to show it to you. Why does that work? Because of that right there. It's a law. It's called the law of large numbers. Okay? The law of large numbers states this, that the greater the number of trials, the closer the experimental probability will be to the true probability. Go back to the flipping of the coin. Yeah, I got 2/3. Okay, and then if I keep doing it over and over and over and over again, eventually it's gonna get closer and closer and closer to 50%. It's not a suggestion, it's not a hint, this is not me making things up. It is a provable mathematical law, okay, that will happen. So, why do casinos do what they do? She goes in and plays. She wins the jackpot. There you go. And you're right. If a casino had one, just one, that's probably going to be a losing proposition for them. But I think, and when I did this about a year ago, MGM Grand, I think, was the largest casino in Las Vegas. Slot machines. In their casino, they had 500,000 slot machines. The average person can play 800 games an hour. And they're open 24 hours a day, 365 days a year. How many trials are happening now? Look at that number. So all of those large numbers are adding up, right? And so that's why there's that edge. So when you hear a casino say, man, we've only got a 0.001% edge on this game. Well, yeah, but when you're playing billions and billions and billions of trials, well, do 0.01 of the $1.2 trillion that people spent last year on gambling, and you'll see why. They're like, please, we don't mind that 0.01 edge. And that's all probabilities, and that's just casinos. Other things run off that. It's the easiest one that people will kind of see. That's okay. I am not against gambling. Okay, so don't take this and go, man, I teacher did just preach against gambling. No, I'm trying to show you the math behind it, is all I'm doing. And then lastly, just for clarification, there's a thing called the gambler's fallacy. The gambler's fallacy is an erroneous belief that a random event is less or more likely to happen based on the results from a previous series of events. Here's how it works. I'm flipping a coin over and over and over again, and he's waiting over here, or she's waiting, and I flip like 10 heads in a row. Okay? And then all of a sudden, okay, he goes, I'll bet you $100. The next one's gonna be a tails. And I go, why? He goes, because it has to be. Why? Look how many heads you got. What's the probability of me getting a heads or tails? It's still 50-50. That quarter does not care about everything that happened. It doesn't hold a memory and go, man, I forgot. I've done a lot of tails. I've done a lot of heads. I've now got to give a tails. It's just only fair. There's the definition of random, if you kind of think about it. Nothing acted on the outcome of the next event. It's completely random. It's still 50-50. Okay. So the gambler's fallacy does say that because this has happened, this has to happen. When in actuality, no, it doesn't. It doesn't at all. Okay. Good. How do we feel about probabilities? Let me show you the rule of large numbers real fast. And then I'll do a couple of your homework examples. Look here. We have 2 dice being rolled. When I roll a 1 and a 1, I get a 2. When I get a 2 and a 2, I get a 4. No, this is just a sum table, right? Okay. I can come up with an outcome space, right? Total outcomes will be what? 1, 2, 3, 4, 5, 6. Just 6 times 6. So my total number of outcomes is what? 36. So what is the probability of me rolling a sum of 2? Very good. 1 out of 36. Not too hard, is it? Let me show you something. What if I just take the dice? Now, mind you, these rolls are gonna be the sums, okay? So I pick up 2 dice, I roll it. I do it 4 times. There you go. On my first roll, I got a sum of 3. On my second roll, I got a sum of 5. On this one, I got an 8. On this one, I got 11. Notice up here, that's saying I only did this 4 times. There's 100 times. Look what's happening. Still isn't perfect though, is it? There's 10,000. Here's a minute. Look how it just started to match. The larger it goes up, and you're never gonna see anything jump after this point. Notice, if you actually did the math for this right there, that's where the percentage will work out. Kind of weird how that works, huh? But it is a mathematical fact that happens. Okay, hence why we call this the law of large numbers. As the numbers increase, as the numbers of trials in your experiment grow, it will start to match the classical probability, if there's a classical probability to match it to. Okay, that kind of help you out a little bit? Okay. Let's do some pops. A coin is tossed 7 times, okay? This might harken back to something we just did. Okay, what is the probability of getting all heads? Express your answer as a simplified fraction or as a decimal rounded, okay? So what would that be? First off, how many outcomes? 2, right? No, not 7. Think about outcomes. Outcomes, think of it this way. I've got a coin. How many outcomes can I possibly have? I can only have a heads or a tails. So that's how come I'm gonna put a 2 down. Remember, that's my outcomes. Your exponent is the number of trials you're doing. Okay? So that right there, number of trials. Okay? So what do we get when I get 2 to the power of 7? 40. Hit 2. On your calculator, you do this, hit the 2. There's a little button, a hat button. Okay? And then you hit the 7 key. Okay? That gives you 2 to the power of 7. Okay? You should get 128. Notice, that's my total outcomes, correct? Okay? So where does that number go? On the bottom or the top? Bottom. Well, how many ways is there for me to get all heads? Just one way, right? Like if you were doing that tree diagram, think about it, there's only one way, and that's going up the top line of it. I can't waver off ever because that means I got a tails in there somewhere. So there's only one way. That's not horrible, is it? Pretty straightforward. A telemarketer's computer selects phone numbers at random. And when you want to hear random, think computer, because you are not random. Okay? The telemarketer has recorded the number of respondents in each age bracket for one evening in the following table. What is the probability that the next respondent will be between 26 and 45? Once again, enters a fraction or a decimal rounded to 4 decimal places. What should be the thing, if I were you, that I would do first every single time? Find what? Total outcome. Exactly. Find your total outcomes. How would I do that?
Add them all together.
Yeah, look at this. Take all these guys, add them up. Exactly. That's your total outcome. Because those are all of the calls that happen. That's my universe. That's what I have to choose from. That's like me going to Albertsons going, what do I have to shop for? In here. My wife told me cereal. Narrow my universe. The store is the universe, but the one I need to look at for my numerator would be where I narrowed it. Here, my universe is all the calls. That's for my outcomes on the bottom, which I can put as What is it? When you do the math of that? 201. But now I've got to narrow my universe down. I can't just look at all the calls anymore. I have to just look at some specific calls. Specific calls that are bounded in where?
6 to 45.
Yeah, this one and this one because of that 45. And so I would come in here and add the 40 plus 57. Do the math of that, and you're gonna get 97 all over 201, which will turn into 0.4826. What else could I call that probably? Remember what I called it earlier? Coin flip. Remember, because it's almost 50%, I say, hey, what's the probability this thing's gonna happen? That's coin flip, it's about 50%. Okay? A box contains 97 red marbles, 54 white marbles, and 14 blue marbles. If a marble is randomly selected from the box, what is the probability that, ooh, look at that, it is not red? And once again, express your answer in the prescribed method. What do I have to do first? Add up my universe. What's everything I can choose? Well, it's gonna be the 97 plus 54 plus 14 all over. Okay, be very careful now because they're going to try to trick you in HOPS a lot by the word not. Sometimes they will say that to you, okay? But notice on this one, since they're saying not red, I can't count the red anymore. So it's gonna end up being just be the 54 plus 14. Do the math of that, you get 68 over 165. And that's equal to 0.412. There's a couple of more on here, they're in your notes. Very simple ones, run just like that one. Next class, we'll probably go over we're gonna go over 4.2 and 4.3. I highly suggest now 4.2, 4.1 and 4.2 is all that's due next week. Okay, by the end of the week, but because of the test, I still want to get us ahead a little bit. Okay, one, it'll give us a day to kind of review for the midterm a little bit, whenever that gets a little bit closer. Don't forget, I'm also going to be gone in March for a day. So that gets us also, make sure we're a little bit ahead for that, because I don't ever want you to feel like you missed a class or missed a learning. So by tomorrow afternoon, all the lectures for this week will be posted online. So you feel like you missed anything or you need to hear something again, they're there, go in and click on it. Feel free to look and then email me if you ever want anything.